only thing that's constant is change. Whoever it was that coined this phrase was positively correct. And that's one reason why the chemistry of our environment is so very fascinating. We've already seen how time and chemical energy have altered the composition and behavior of the land, the sea, and the subsurface of the earth, all the way down to the core itself. But change in our environment doesn't stop there. In fact, it gets even more exciting as we continue to move outward into the atmosphere. Why? Because the forces acting on the planet itself, though incredibly powerful, tend to fuel processes so slow that they're difficult to observe in a human lifetime. But as we move into the gas phase and begin considering how and why our atmosphere behaves, processes can take place much more rapidly. But before we dive into the chemistry of this relatively small slice of our environment, let's get familiar with its structure. Our atmosphere, much like our oceans, is relatively uniform. It's undergone some significant changes over geological time, like the slow conversion from reducing to oxidizing conditions that led to the banded iron formations that we discussed previously. But truth be told, over the past few billion years, very little has changed. Once the major transition to an oxidizing atmosphere was complete, courtesy of the evolution and growth of bacterial organisms, it has remained remarkably steady. Our atmosphere is comprised primarily by just two gases, molecular nitrogen at 78%, and molecular oxygen making up about 21%. Just about anywhere you go on the surface of the Earth, you will find this ratio of nitrogen and oxygen. Nitrogen, of course, is essentially inert. In the case of the atmosphere, we can usually think of it as little more than a solvent, diluting other gases that drive the chemistry of the atmosphere. And oxygen, of course, plays its role in many processes and is always present as well, at least in recent geologic time. But it's that remaining 1% that really spices up the chemistry of the atmosphere. After centuries of study, mankind has come to understand the powerful and complex chemistry that goes on in the atmosphere, and much of it is driven by those few remaining gases making up the balance. Water vapor is special because of how rapidly and widely its concentration can change. Because the boiling point of water is so close to the temperatures that we encounter here on Earth, minor fluctuations in air temperature can have a significant effect on just how much water vapor the air can hold. We've all experienced this. Just compare the difference in a humid day in summer when warm air is saturated with water vapor against a cool winter's day when very little moisture can be dissolved. On those days, even our best efforts to compensate using humidifiers rarely succeed. In the meantime, carbon dioxide is also a changing component of the air around us. Somewhat different than water, carbon dioxide levels rise and fall over much longer timescales, affected by seasonal plant activity and human use of fossil fuels over the years. Then there are other gases that find their way into our atmosphere. Gases like sulfur dioxide and nitrogen oxides, which can be released into the air via coal-fueled industrial plants, or from geological sources like volcanic eruptions, or even lightning strikes. These gases tend to react on release and don't have an opportunity to spread globally. Instead, they alter the chemistry of smaller pockets of the atmosphere, sometimes with significant consequences. Today's lecture is going to focus on all of these players as we seek to understand how the atmosphere is structured and how, even though we generally spend most of our lives living under it, the chemistry of the atmosphere at all altitudes can have a profound effect on our lives. Imagine the atmosphere is an ocean, and we are the creatures living on the floor of that ocean. It isn't that far from the truth. And as the 1800s came to a close, many curious researchers were out to discover what secrets lay just above our heads in plain sight, but out of reach. One of the first of these was Léon-Philippe Tesserand-Debord. Debord was one of a group of pioneering researchers whose mantra was simple. If you can't bring the upper atmosphere to your instruments, send your instruments to the upper atmosphere. In the latter half of the 1890s, Debord launched hydrogen weather balloons from the weather station that he had founded in Treps, France. Now, this was just outside of Paris, and his balloons were carried aloft by the buoyancy of hydrogen, and they were armed with a clever mechanical device. It was designed to tear the base of the balloon after a period of time, sending it back to Earth using the top of the balloon as a parachute to slow descent and protect its payload. Its payload was bottles designed to trap samples of the air aloft, as well as some of the first self-recording instruments. He set out to measure values like humidity and composition, which could be determined by analyzing the trapped samples after the flight. But other parameters, including temperature, the bit of data that would earn him immortality in meteorological science, were a bit trickier. Temperature had to be measured during the flight. So his balloons carried a cleverly designed thermometer. It was made of various metal wires, each of which expanded and contracted in response to temperature. Now, by attaching these wires to a pen, his thermometer would automatically record the temperature as a trace created by the moving pen. This trace would then be reviewed after the balloon was retrieved. Now, though very simple, de Boer's temperature data were fascinating. Initially, he found that temperatures gradually and steadily dropped with higher altitude. It's no big surprise there. As pressure drops, one would expect temperature to drop as well, in accordance with Charles' law. But as the balloon flights exceeded altitudes of 10 kilometers, about 6 miles up, the temperature change stopped. From that point forward, no matter how much higher he flew his balloons, the temperature remained constant. At about 10 kilometers, something obviously changes, not gradually, but very suddenly. De Boer published his findings in 1902, calling the lower layer of the atmosphere the troposphere and the higher layer the stratosphere. His discovery changed the way scientists think about the atmosphere, how it moves, and what it's made from. As we'll soon see, the chemistry of these two layers can be quite different, though equally important to the health of our environment. The obvious question that arises from de Boer's experiments is, why? Why does the temperature suddenly stop dropping as the stratosphere is reached? His countrymen, Joseph Louis Gay-Lussac and Jacques Charles, had clearly shown more than a century earlier temperatures should decrease with altitude as the atmosphere thinned, unless there must be an external source of energy, something pouring energy into the outer reaches of the atmosphere. There was, of course, and the answer was clear as the sun. The answer was the sun itself. The sun emits a powerful mixture of electromagnetic radiation over a broad range of wavelengths. The visible and infrared wavelengths, it would appear, traverse the atmosphere with little problem, reaching the ground and bathing us in the heat and light that we have all come to expect from our benevolent local star. But not all that comes from the sun is beneficial to us. In addition to the visible and infrared light, the sun also releases a stream of ultraviolet radiation. The shorter ultraviolet radiation means that photons of this class of light carry more energy than their visible counterparts. Enough energy to promote the breaking of bonds critical to holding our DNA together, so it can cause cellular damage when it reaches our skin. Fortunately for us, the worst of this radiation, called UVC radiation, never gets to the surface. Instead, it's absorbed by a protective layer of a very special type of triatomic molecular oxygen, O3, also known as ozone. Now, ozone had been observed in the stratosphere as early as 1913, but its critical role in protecting Earth wasn't realized until about a decade later. A British researcher by the name of Dobson, taking advantage of more precise thermometer technology, was able to show that the stratosphere temperature is actually not constant, as de Boer had believed, but it actually was slightly inverted. By this I mean that the temperature actually increases with altitude in the stratosphere. This so-called temperature inversion, coupled with the discovery of high concentrations of ozone, painted an unmistakable picture. Ozone was absorbing radiation from the sun, making it slightly warmer at the top of the stratosphere where the radiation was strongest. Now, realizing how critical this absorption of UVC by ozone is to our plant's health, Dobson set about creating a device that could be used to monitor its concentration at a specific location. His device has come to be known as a Dobson meter. It works by measuring not UVC radiation, that's all absorbed in the upper atmosphere, but rather UVB and UVA radiation. Now, recall that ozone doesn't absorb UVA radiation at all, but it does partially absorb UVB. Now remember that Bayer's law says that the intensity of a compound's absorption at a given wavelength is proportional to its concentration in the sample. So now Dobson's invention starts to make some sense. Using the UVA intensity as an internal standard, the Dobson meter measures the intensity of UVB radiation and compares it to that standard. As the ozone level drops, the intensity of UVB radiation relative to UVA radiation increases in accordance with Bayer's law. Using Dobson's invention, atmospheric scientists could detect thinning ozone before it became so depleted that UVC started to penetrate, making the problem life-threatening. And it's a good thing, because in 1984, a group of 3 British scientists, Joseph Farman, Brian Gardner, and Jonathan Shanklin, made a very startling and very unsettling discovery. They were Antarctic explorers in a certain sense of the term. Not the intrepid fur-clad type of explorer trekking across the frozen surface of the continent, but rather they were exploring the atmosphere above Antarctica. What they discovered was that a region of the ozone layer nearly the size of Antarctica had thinned substantially, bathing the continent in high-energy UVC and UVB radiation. Years of mapping this thin layer has revealed that each year it seems to grow a bit larger and larger. Now, clearly, something was changing for the worse here. But why? The answer to many was clear. A class of compounds called chlorofluorocarbons, or CFCs, was to blame. You may remember that chlorofluorocarbons, like Freon, are a class of chemical compounds invented by Thomas Midgley in 1930. That was the fateful year that Midgley and his team, tasked with developing a newer, better refrigerant, thought that they had found the perfect product. Midgley's team created dichloro-difluoromethane, a compound that had all of the desired volatility of a refrigerant with the added benefit of being non-flammable, non-toxic, and completely unreactive. Or so he thought. The tragic flaw with Midgley's Freon was that it only appeared to be unreactive. Midgley and his team were correct that Freon and compounds like it were unreactive under conditions encountered down here, at the base of the troposphere. But when allowed to vaporize in the open, say when leaking from a refrigeration unit, these volatile compounds rise and are carried aloft by air currents. And when they reach the stratosphere, things change. The critical bond is this one, the carbon-chlorine bond. Stable and unreactive under surface conditions, when these bonds reach the stratosphere and are exposed to ultraviolet light, that carbon-chlorine bond can break with devastating consequences. Before we consider the effects of having chlorine atoms in the upper atmosphere, let's first consider a healthy chemistry that's going on in the upper atmosphere. The Earth's upper atmosphere contains, among other things, a protective layer of ozone, which is O3 gas. But that's not all that's up there. In fact, the presence of ozone is due to an equilibrium process between atomic oxygen and ozone forming diatomic oxygen, which then can convert back into ozone again in the upper atmosphere. This is not a static situation. It's an equilibrium process in which ozone is constantly breaking down and being reformed as these two reactions run backward and forward together in an equilibrium. So, in a healthy upper atmosphere, there's always a certain concentration of ozone gas present to absorb ultraviolet radiation. But what happens when we set an imbalance to that chemistry? Well, let's think about that. Again, we have our healthy equilibrium here between atomic oxygen and ozone forming diatomic oxygen and back again. But let's add one extra thing to this equilibrium. Let's add a chlorofluorocarbon. In this case, I've used Freon 12. Now, Freon 12 can act as a source of chlorine atoms, and chlorine atoms can act as a catalyst on our equilibrium, changing the rates at which this reaction takes place. What's worse is, it catalyzes the forward reaction, but not the backward reaction. In other words, the presence of that chlorine atom causes ozone and atomic oxygen to form more diatomic oxygen, but it does not accelerate the reformation of that ozone. And this is the source of ozone depletion. The specifics of the chemistry go like this. The carbon-chlorine bond is very stable near the surface of the Earth. So when chlorofluorocarbons were first developed, there was no reason to suspect that they would be potentially so dangerous. But when you get into the upper layers of the atmosphere, there is higher energy light available. Photons with enough energy, enough of a quanta of energy to break that carbon-chlorine bond. Here comes one now. It just broke my carbon-chlorine bond, releasing a chlorine atom, which has only 7 valence electrons. It's very, very reactive. So, put in the presence of ozone, this chlorine atom will very rapidly steal an oxygen atom away, and in doing so, form chlorine monoxide and a molecule of oxygen. Now, that would be bad enough, right? If one chlorine atom could destroy one molecule of ozone. But the truth is actually much, much worse than this. You see, that chlorine monoxide can go on to react with atomic oxygen, another species that we know to be prevalent in the upper atmosphere. And in doing so, it creates another molecule of O2, and it also regenerates the chlorine atom. This is why it's a catalyst in our reaction. And that chlorine atom can go on to catalyze the decomposition of not just one, but many, many hundreds or even thousands of ozone molecules before it's finally consumed in a scavenging process. So this is why we have to be extraordinarily careful about releasing CFCs into the environment, because very small amounts can do a great deal of damage. So the bad news is that over the 50 or 60 years that humanity dispensed these chemicals into the atmosphere with abandon, we were unwittingly destroying a critical protective layer of our own atmosphere. Now, the good news, however, is that we realized our mistake in time. And as use of these compounds has decreased, the ozone layer's natural equilibrium seems to have started to reestablish itself. We may not be there yet, but after the calamitous growth through the 1980s, the hole has maintained a nearly constant size ever since. Now the world watches and waits to see if the hole will naturally begin to heal itself as the CFCs are slowly purged from the upper atmosphere. But ozone's story doesn't end there. So far, I've made ozone seem like a benevolent protector of humanity, floating far away in the stratosphere looking over us. And make no mistake, it does just that. But ozone is a bit of a Jekyll and Hyde among molecules. As beneficial as ozone is to humanity in the stratosphere, it can be every bit as dangerous to us down here in the troposphere. And while we were busy destroying it in the stratosphere for most of the 1900s, we were also busy creating it down here, where we work, play, and live. We largely have our own voracious appetite for fossil fuel energy to blame for the phenomenon of what is known as photochemical smog. Smog, a combination of the terms smoke and fog, was first described in the 1950s. At first, it was a curiosity, but it rapidly became a plague to low-lying areas with significantly higher terrain surrounding them, areas like Los Angeles, California, for example. We've all seen it before, that thick, hazy, fog-like gas creeping across the iconic Los Angeles landscape. A brown haze that creates a burning sensation in the lungs when it's inhaled. Now, by the 1960s, smog was considered a standard part of life in places like this. And why not? It was a strange environmental phenomenon indeed, but smog was a thick brownish color cloud of vapor with an acrid odor when inhaled, and auto exhaust was none of these things. It was a clear stream of oxides and water vapor created in a combustion process, right? Well, unfortunately, this idea was wrong. There was a very serious connection between the two. As automobile production in the US continued to grow, so did automobile emissions. And a problem that no one even realized existed at first grew right along with it. The problem was ozone, but no one suspected it. And why would they? This relatively recently discovered atmospheric helper was a component of the upper atmosphere, the stratosphere, not our neck of the woods at all. How wrong we were. It turns out that an unintended consequence of a product of our own design, automobiles, was to blame for the global problem of smog. The chemistry behind the problem of photochemical smog begins with any old gasoline or diesel burning vehicle. So let's bring in the back end of one of those here. So here's your exhaust pipe from a vehicle that's burning fossil fuels. Now, we know that when we start up those vehicles, we generate emissions. And we also know that in an ideal world, we would only be generating a few different types of emissions. Carbon dioxide, carbon monoxide, and water vapor as a result of oxidation of hydrocarbons. Now, these gases all play their own role in environmental chemistry, but the truth is that they're not the only thing that's emitted in this process, that there are impurities in the gasoline, some of which create other emissions products, like NO gas. Now, nitric oxide gas is particularly bad because it's fairly reactive, and it can undergo a reaction with the oxygen in our atmosphere down here at the ground level. When it does that, it reacts to form NO2 and something that we're familiar with seeing, atomic oxygen. But atomic oxygen doesn't have a place down here on the surface. It serves us well in the upper atmosphere, but at the surface of the Earth, it undergoes additional chemical reactions, most notably with another molecule of molecular oxygen to form, there it is, ozone, down here at ground level, where we know ozone can undergo a number of different chemical reactions. Of course, the difference here is that the ozone formed in this process is not tens of kilometers above our heads. It's right in our faces, quite literally. Inhalation of ozone is an all-around bad idea. As helpful as it is in the stratosphere, in our lungs, it is very bad news. Ozone is not very water-soluble, so unlike the more primitive chemical weapons we discussed, like sulfur oxides and chlorine gas, it penetrates deep within the lungs. There, in the natural fluid present, it finally does dissolve and reacts with a number of biologically relevant compounds. Last time we discussed how important the pH levels of oceans are. Recall that we discussed how oceans can absorb atmospheric nonmetal oxides, becoming acidified and potentially disrupting chemical processes essential to life there. You might have thought to yourself, gee, I'm glad I don't live in the ocean so I don't have to worry about that kind of thing. Well, not so fast. In the mid-1800s, as the Industrial Revolution gained momentum, a Scottish chemist by the name of Robert Angus Smith made an important observation. Angus had earned his PhD with another famous chemist, Justus von Liebig, the father of modern agricultural chemistry. And perhaps that training had made him particularly sensitive to the effects that chemicals can have on the health of plants. But when Smith returned from his studies, he noticed that forests downwind of the most industrialized regions of England seemed to be suffering. Smith set out to find out what was happening. He had a very good idea, as he'd also observed that iron roofing seemed to rust faster on buildings closer to industrial districts. Now, this keen observation led him to hypothesize, since it was well known at the time that acidic solutions could accelerate the oxidation of iron, that acid in the atmosphere was to blame not only for the early demise of the roofing, but for the troubled forests as well. Now, Smith's work predated the development of the pH scale by Søren Sørensen. So his measurements were reported as the amount of mineral acid he could recover from samples. But to translate his results into the pH scale, meteoric water often has a pH of about 5.5 to 5.6. This mild acidity comes from the hydration of atmospheric carbon dioxide in contact with water droplets as they form rain. This little bit of acid is a good thing. It facilitates the chemical weathering of certain rock formations, carrying nutrients into rivers and lakes, as well as driving geologic processes. The problem was that carbon dioxide wasn't the only nonmetal oxide gas in the atmosphere of industrial England. The byproducts of coal-fueled power plants, for example, contain sulfur oxide compounds, most notably sulfur dioxide. So what's a little bit more nonmetal oxide gas in the atmosphere, right? With all the carbon dioxide naturally present, how can just a pinch of SO2 from a power plant or volcanic eruption be enough to cause a problem? Well, the answer to that question lies in the strength of the acids that form. Now, the burning of naturally occurring fossil fuels like coal, of course, releases a number of species just like our automobiles do. It releases carbon dioxide, releases some carbon monoxide, but it also releases, in many cases, sulfur dioxide. Now, sulfur dioxide forms because most naturally occurring coals have a certain amount of sulfur-containing compounds contained inside of them. And those are the ones that we really have to worry about. Because when sulfur dioxide reacts with moisture in the atmosphere, even here near ground level, a potentially dangerous reaction happens. It creates a molecule of H2SO3, sulfurous acid. A weak acid, yes, but a weak acid with a pKa of somewhere around 2. Now keep in mind that the pKa of carbonic acid, which forms naturally as a result of carbon dioxide, is well above 5. But that's not the worst part. Whatever SO2 makes it into the upper atmosphere, where it can be exposed to atomic oxygen, can undergo yet another reaction in which it creates sulfuric acid, a strong acid, thereby increasing the acidity of the rain that falls down here on the Earth, where we would really like things to not get too terribly upset chemically. So the burning of coal has created a potentially dangerous situation in the form of what we know as acid rain. So even under the best of conditions, sulfur dioxide hydrates to form an acid molecule that's about 10,000 times more acidic than the carbonic acid that's naturally present in rainwater. Smith realized that it was this sulfur dioxide and other compounds like it emitted from smokestacks of industrialized England that were devastating the forests nearby. He termed the phenomenon acid rain in his 1872 book, Air and Rain, The Beginnings of Chemical Climatology. Even in modern times, the specter of acid rain looms as an environmental problem waiting to happen. Remarkably, it took more than 100 years for the true dangers of acid rain to be recognized as an environmental threat worthy of action by the U.S. government. In 1978, the recently created Environmental Protection Agency measured an acid rain pH of 1.5 in Wheeling, West Virginia. That is 10,000 times more acidic than ordinary rain. In 1990, after a decade-long study, it was determined that many lakes and streams, particularly in the northeastern U.S. and mid-Atlantic regions, were beginning to become so acidic from rains like this that they could no longer support native fishes. Congress acted very swiftly after that, mandating reductions in sulfur oxide emissions from power plants and other major sources across the country. Modern power plants that burn coal take several steps now to reduce their sulfur emissions, one of which focuses on removal of the sulfur dioxide gases, for example, by chemical scrubbing. So let's summarize what we talked about in this lecture. We started by thinking about the atmosphere, acknowledging that it's a pretty stable environment consisting primarily of nitrogen and oxygen gases. Then we met Léon-Philippe Tesserand-de-Boer, whose pioneering balloon experiments led to the discovery of a zone of temperature inversion, which he called the stratosphere. We saw how the stratosphere has some fundamental chemical differences from the troposphere. Most notably, a layer of ozone which absorbs UVC and some UVB radiation, protecting us from this damaging light and creating a temperature inversion zone which led to the stratosphere's discovery in the first place. Then we considered the famous ozone hole that opened up over Antarctica as a result of chlorofluorocarbon use for about 10 decades. We saw how the carbon-chlorine bond from Midgley's invention breaks at high altitudes, releasing a catalyst which devastates the natural equilibrium that maintains our protective ozone layer. Next, we took a look at ozone near the surface, where it is far less welcome. Here, complex reactions between nitrogen oxides and other components of air create ozone at the surface, where it attacks our lungs rather than protecting our skin as it does in the upper stratosphere. Then we turned our attention to another serious environmental issue of our time, acid rain. We met Robert Angus Smith, who pieced together a theory connecting industrial smokestack emissions to weathering of buildings and damage to forests and crops in 1850s England. We saw how his warnings went largely unheeded for more than a century, when rain 10,000 times more acidic than normal finally prompted government action to protect us from this dangerous phenomenon. As we pass out of the upper atmosphere, we're about to leave Earth behind. Our final lecture will carry us into the reaches of our solar system and beyond as we discuss the chemistry of the cosmos. Join me for the longest leg of our journey next time.